In this video I want to go over the in-class Lecture 6 quiz, the in-class quiz on Chapter 6 of your textbook. So number 1, 2 contributions to the electric potential at a particular point in space. Electric potential. How do you combine them to get the total electric potential at the point in space? The electric potential, phi, is a scalar, not a vector. And scalar contributions, they correspond to two numbers. You add them like scalars. So that would be A. Add them like vectors is definitely wrong. Take the average, that's wrong. Square root of the sum of the squares, that's wrong. So, yeah, definitely A. Add them like scalars. Only possible answer. Then, given two positively charged particles, each fixed at a different point in space with a finite separation between the two, are there any positions on the line passing through both particles other than at infinity at which the electric potential due to the two particles is zero? Okay, the individual contributions go like phi 1, for instance, is equal to k q1 over r 1 to p. So where point p is some point in space that you're investigating to see where they might add up to 0, where the total electric potential might be 0. q1 is positive, and therefore phi 1 is positive. Phi 2 is going to be equal to k, so lowercase k, q2 over r2 to p. So the phi due to the second charged particle at the empty point in space under consideration p, and q2 is positive, so phi 2 is positive. So we're trying to find two positive numbers that when you add together them you get 0, and there are no such positive numbers. And we're talking about other than at infinity. At infinity, both pieces would actually be 0, and the limit as r1p goes to infinity, phi 1 becomes 0, likewise over here for phi 2. So at infinity we could say the electric potential is 0, but the question specifies other than at infinity, and so no, there are no places at which the electric potential due to the two particles is 0. Electric field, yes, they add like vectors in between the particles. You get some cancellation, so it could be 0 and will be 0 at a point in between. But electric potential, no. And then consider 2 points, A and B, in the vicinity of a positively charged particle where B is farther from the particle than at A, at which point is the electric potential greater. And I would say A is closer, so it's greater there. In other words, phi goes like kq over r. The smaller r is, the bigger phi is. Q is positive, so we're dealing strictly with positive numbers. Because we're talking about a positively charged particle. So fixed in space, point A is closer, and therefore for point A, the separation between the empty point in space and the position of the charged particle is smaller, and the smaller the denominator, the bigger the value. So phi is greater at point A. That concludes our video on the in-class quiz on Chapter 6.